This is a video of the 6 trig functions. We only know of 3 so far, and so what's on the screen should look somewhat familiar from the previous class. The trig functions, sine, cosine, and tangent, take an angle as an input. So the function is, sine of theta, just like f of x, kind of. And they're always equal to their same specific ratios. So sine is always equal to, in a triangle, the opposite side over the hypotenuse based on where theta is. So in this particular triangle, I have theta being this left corner. It has to be a right triangle, so one of the other angles is 90 right here. And the other angle I'm not really concerned about because I called this one theta. So based on where theta is, that makes the orientation of the triangle. So like across or opposite side of the triangle, where theta is, opposite that is the opposite side. And the long side is always a hypotenuse regardless of where theta is. And then adjacent is the other side that's next to theta. That's not the hypotenuse. So sine is always equal to opposite over hypotenuse. Cosine of theta is always equal to adjacent over hypotenuse. And then tangent of theta is always equal to opposite over adjacent. So it's a brief review. And those acronyms, SOH-CAH-TOA, kind of, they just categorize which trig function gets which side length, the ratio of their side lengths. So SOH-CAH-TOA. Notice that CAH means cosine of theta equals adjacent over hypotenuse, and so forth. Okay, so that's what we should know up to this point, walking into this unit. And then just a quick note about theta. Theta is just a variable like x. It's a Greek letter, so it is a letter or variable. And we always use those for angles. We could also use different Greek letters like alpha and beta. We may see those later on, but for right now, just theta is an angle measurement. All right. The other 3 trig ratios that we have not seen before are cosecant, secant, and cotangent. So I can write those down, but they're called the reciprocal trig ratios because they are reciprocals of sine, cosine, and tangent. So as sine, we know is opposite over hypotenuse. Cosecant, spelled like this, is the hypotenuse over the opposite. It's just the reciprocal of sine. This could be a little confusing, and you'll see why in a second. It's because sine is paired with cosecant, whereas cosine of theta, being the adjacent over the hypotenuse, is paired with, or is the reciprocal of secant. So you can kind of see how it's a little counterintuitive, where sine and cosecant are together and cosine and secant are together. It would make the world would be easier if the cosines and the cosecant were together, but whatever. So this is hypotenuse over adjacent. And then tangent, fittingly, is paired with cotangent. So these are always the case. This is opposite over adjacent, and that makes cotangent be adjacent over opposite. So now we have 6 trig ratios. These all have to be dealt with, dealing with a right triangle, and they're always equal to these specific ratios. The cotangent will always be adjacent over hypotenuse, for instance. Tangent. Okay. Next, here are some examples. So if we know that secant of theta is 6/5, then we know since secant is paired with cosine, then cosine is just straight up the reciprocal. So that one can't get easier than that. The next one, it says sine of theta is 0.8. So cosecant of theta is going to be the reciprocal of that. So we may need to turn 0.8 into a fraction, which is not super difficult. 8 tenths, 0.8 is 8 tenths. And that could be reduced to 4/5. And that means then, because sine and cosecant are paired, they're straight up reciprocals, so 5/4. All right, it's cruising. So let's say we have a triangle, and in this particular one, we have two sides that are known. We do not know the third side. This is where we'd have to use Pythagorean's theorem. We could technically use SOH-CAH-TOA to figure out an angle, and then use that angle to figure out the hypotenuse using just all trigonometry, trig functions that we haven't reviewed yet, but we could just use Pythagorean's theorem. So it's a squared plus b squared equals c squared. C is the long side. And I will say this triangle isn't very appropriately labeled. I'm noticing, because if I want to call side C the hypotenuse, then the angle opposite it should be capital C. Triangles always operate that way. So, capital A over here, the side opposite it should be lowercase a. Same letter, just lowercase. Sides are lowercase. And then this should be B, and this should be lowercase b because it's opposite angle B. But it doesn't need, we don't need to label it so that C is the hypotenuse all the time, just to use Pythagorean's theorem. Like we could, as long as we know that in the formula, the hypotenuse side length is on the other side of the equal sign. Anyway, so hope that wasn't too confusing. That'd be 8 squared plus 15 squared equals c squared. And then we just gotta solve this. So 64 and 15 squared is 225. Equals c squared. And then to solve for c, to get that actual length, we need to square root it. Because it's c squared, we need to just have c. So square root of 289, I believe, is 17. Okay, all of that work using Pythagoras theorem, maybe it's less familiar these days. You haven't used it in a while, but this isn't really much to do with the problem. We just needed to get that third side length before we can actually write the trig ratios. The 6 trig ratios, I just set them up because those are the ones we're needing to find. Sine of A, cosine of A, tangent of A, cosecant of A, secant of A, and cotangent of A. So trig ratios, I obviously start with sine, cosine, and tangent because those are the most familiar. Opposite hypotenuse from A is right here. So opposite is 8, hypotenuse is 17. And because I now know sine, I can knock out cosecant right away too. That's 17 over 8. All right, so this is basically just flipping the fraction. It's just taking the reciprocal and knowing which trig ratio, which trig function is paired with which. Cosine of A is adjacent over hypotenuse, so 15 over 17. Again, 17 is hypotenuse because it's the longest side. 15 is adjacent because it's next to A that's not the hypotenuse. And then secant of A is just the reciprocal. Finally, tangent and cotangent, opposite over adjacent is tangent. So that would be opposite of A is 8, adjacent is 15, so 8/15. And then cotangent is 15/8. So it's pretty easy once you get the hang of it, but there is a lot of prior knowledge required to make this. Well, it's not really a leap; it's a short step. Just taking the reciprocal, knowing it's paired, knowing which ones are paired with which, and what they are. CSC is cosecant, so on. All right. Here's another example. This is a little bit different because in this triangle we aren't given a side length, just like the last one, but we are given the hypotenuse. So the side length we don't know is one of the legs. And this triangle is appropriately labeled in that angle C is the 90-degree angle, and so side C is the hypotenuse, so it does fit with the way Pythagorean's theorem is set up already. This would be side A. So we'd have a squared plus b squared. B is 6 squared, and then c squared is 20 squared. Solving this is a little bit different. We just need to, it's just a regular equation. You just solve for a. So 6 squared is 36. 20 squared is 400. A squared is a squared. All right, we need to get a by itself, or a squared by itself. So we're moving the 36 across by subtracting, just adding the opposite. We end up with a squared is equal to 364. All right, and then to actually solve for a, instead of having a squared, we would need to take the square root of 364. Now, if you recall, one thing we know is if I try to take the square root of that, I'm going to get a unfriendly decimal. Recall back when we did radicals, we need to find a perfect square that 364 is divisible by. We also, that would split it into the multiplication of two radicals, and then one of those ideally being a perfect square. If you can't visualize this, that's okay. One other way that we did it was we did prime factorization. So I'll do that here just to see if we remember it, but whichever way works for you is fine. I know that 364 ends in an even number, so I could, these are all square roots, by the way, but I'm basically breaking it down into the multiplication of the smallest pieces that multiply to be 364. So that would be 2, and if you divide, you get 182. 2 is a prime number, so I'm going to stop there, and then 182 is also divisible by 2. And 91 is what's left over. So basically, we're going to have to stop there because 91 is a prime number. 2 is a prime number. They're not divisible by anything other than 1 in themselves. So what we end up with is 2 times 2 times 91 is 364. But I do have a pair here. Because we have a pair, basically what we just found out is if I basically found out that 2 times 2 is 4. We know that 4 times 91 is 364, and 4 is a perfect square. So I would say 364 is the multiplication of square root of 4 times square root of 91, and square root of 4 is actually simplifiable to 2 times square root of 91. So that is us reducing this radical. That was not very fun. Hopefully you don't have to do a ton of those. But that is what that side length is. And this is the reason we do that is to make it look simpler, for one. But this way it's an exact number. As soon as you take the square root of a number that is an irrational number, or that is it's not a perfect square, you're going to get an irrational number. And if it's an irrational number, your calculator is going to chop off the decimals, and it's now an inexact number. So we like to keep the exactitude of numbers, probably not a word, whenever we can. So that's what we have. It's getting worse. Okay. The 6 trig, I have 3 sides now, so I can write the 6 trig functions. We are from the same problem before. We were looking for all the trig ratios from angle A. So that's what it says right here. However, I'm just going to say, I like theta. It's a fun little variable. So I'm going to call angle A is theta. So I'm going to say sine of theta. cosine of theta and tangent of theta. Sine of theta. So theta is opposite over hypotenuse. Sine is opposite over hypotenuse. Opposite of theta is 2 square roots of 91. So this would be opposite over hypotenuse, and that's reducible to the 2 and the 20 would cancel out a 2. So you'd have square root of 91 over 10. That's what sine of theta is equal to. And because I know that, I know what cosecant of theta is. You just flip it. Now, there was a rule in math at one point, excuse me, that you couldn't have a square root on the bottom of a fraction. And we would do something called rationalizing the denominator, multiply basically both top and bottom of the fraction by square root 91. And it would make the bottom then be just 91 without a square root. However, I'm not really worried about that. You can flip it and just leave it. We don't need to do that extra step of simplification. So the other two, cosine, adjacent over hypotenuse is 6 over 20. We can reduce that to, take out 2, it would be 3/10. That means that secant is 10/3. Tangent, opposite over adjacent, is 2 root 91 over 6. You can reduce that, so you get just square root 91 over 3. And so cotangent is 3 over root 91. The correct color. All right, so there's not a whole lot to those types of problems. Let's see if everything's paired all right. First 3 problems are problems just like what we just did. The next 6 problems are like the problems we did right before. Same thing with those ones. All right, we're good. I'll help you out. Here's number 14. If tangent of theta is 1/3, cotangent is 3 over 1. Nice. Let's see. 19, for instance, or yeah, sure. 0.125, you want to change that to a fraction. If you're not sure how to do that, you could use Desmos to do it. You could put 125 over 1,000 because that decimal is 125 thousandths. But using a calculator is just as fast. You'd have to reduce that fraction. Either way, it's 1/8. Just one of those ones you kind of memorize over time. And then secant would be 8 over 1. Or just 8. Cosecant here of 2.5. 2.5 you should change. That's 5/2. And so you would know sign that at that point. All right. All right, hopefully this made sense. It's kind of a review of what the trig functions are for sine, cosine, and tangent. That's what the SOH-CAH-TOA comes in. That's where that comes in. And then we also have now their reciprocal trig functions of cosecant, secant, and tangent. All right, good luck.